So this is chapter 2, part 3, where the book talks about line shape. So to begin with, NMR, when we measure the signal, we get basically intensity versus time. And what you'll see is what we call the free induction decay, or the FID. And this FID, which I didn't draw very well, has an exponential decay. So basically the signal that you see at any one time is equal to the original signal times e to the minus t, where t is time, over t2, which is a relaxation. Well, let's say what we'll call it, the spin relaxation constant. And this constant is different for every hydrogen atom in your molecule. So if you had your good friend ethanol here, then this one would have a different spin constant than this one, and this one. They would all be different. But the important thing here is when you do your Fourier transform, and you go from the time domain to the frequency domain, and you get a peak. This peak, which I didn't draw, is it's hard to do it on this tablet, but it has a line shape that is Lorentzian. Because anytime you Fourier transform an exponential decay, you will get a Lorentzian line shape. And we characterize this peak with V0, its frequency, and maybe h, its height. But most importantly, well, actually, the frequency is the most important. But the second important thing is its width at half height. And in NMR, really, NMR is limited in its capabilities by line width. Because if you have a whole bunch of protons and they're all, stacking on top of each other, it gets hard to interpret stuff just because they have some finite width. And again, this width it comes to really how quickly this decays. So if this decays, so if I draw like two FIDs here, and one decays really rapidly, so I didn't draw, and one takes a long time to decay. This peak is going to be very broad when you do the Fourier transform, and this peak will be very sharp. So the longer it takes to decay, the sharper your peak you will get. And so we'll talk about what determines how quickly it decays. And there's 2 points. There's the inherent relaxation processes that are happening, and also there is the magnetic field inhomogeneity, because you put your sample in a magnetic field, and if the magnetic field is not uniform around your sample, that will cause your signal to decay quicker than it should. And you have just for background purposes, you have a sort of a limited window that you're working on here. So if you have something from 12 to 0 to 12 ppms, is your typical proton window for chemical shifts. And on a 500 megahertz NMR, 1 ppm is going to equal to 500 hertz. And so 12 times 500 is going to be 6,000 hertz, okay? Oops, my pen is sick. Oops, come on. 6,000 hertz. And if you ran it on a much higher field magnet, say a 950 megahertz NMR, where 1 ppm is now equal to 950 hertz, your spectral width, we'll call this the spectral width, is now 11,400 and 11,400 hertz. So you have a lot more hertz to cover your spectrum when you go to the higher magnetic field. So what this does is it basically increases your resolution available. And so that's why when people do biological NMR, they want the highest magnetic fields possible because they want the highest resolution possible. Because they're running stuff like proteins, which basically are consisted of 20 amino acids, and they just keep repeating and repeating. So everything is just stacked on top of each other. And so you want the greatest resolution possible to pull everything apart. Now, the next part is talks about scalar, or what I would call J-coupling. And what this is that one nuclei fills one hydrogen nuclei fills the effect through the chemical bond of another one. So we'll call this guy A, and we'll call this guy B, okay? And so in the absence of scalar coupling, you may see something like this, where this is the peak for A, and this is the peak for B. And so this is the no scalar coupling situation. But that never happens. We always have scalar coupling. And generally you'll always see it when they're three bonds away. You'll have some scalar coupling. And so when scalar coupling is active, what you'll see is something like this, where this peak will be split. And so will this guy. So this peak HA will still be right there, and HB will still be right there, but they're going to be split by some coupling constant, from 1 to 20 hertz, something in that range, depending on the chemical environment. And the easiest way to think of it is A is seeing B in some aligned position with the magnetic field, and one where it's non-aligned with the magnetic field. And so there's one with it aligned and one with it non-aligned. And the splitting pattern that you observe can be predicted by Pascal's triangle. Oops, I forgot one here. And so if there is one neighbor that's causing the splitting, then you would see, we'll circulate, 2 peaks of equal intensity, 1 and 1. If there's 2 neighbors, then you're going to see 3 peaks. So it's something like this. These 2 will be 1 intensity, and this one will be twice the intensity of the other 2. And we call this a triplet, where this is called a doublet, when you have something of this nature. And then if you have 3 nearest neighbors, so this would be like something like here you got H, and you got H, okay? So when you have 3 nearest neighbors, then you're going to get what's called a quartet, where it's a little guy, then 3 times bigger, and then 3 times bigger than a little guy. And so this is a quartet. So something in this situation where you have C, H, H, and H, whereas this is a methyl group. And this would be the C, H, C, H situation. And in general, the number of peaks that you should see is given by this formula. So 2 times the number of the nearest neighbors that are equivalent times the spin quantum number plus 1. So like in the situation of a quartet, you have 2 times 3. Proton is a half plus 1. So that's 6 times a half plus 1. So that's 3 plus 1, which equals 4 peaks. And you see 1, 2, 3, 4. Just as an interesting side note is if anytime you run NMR, you always run it in like a deuterated solvent. Like say you run your sample in deuterated DMSO, which has it's DMSO, which has all of its protons replaced with deuterium. But there's always a little bit of impurity in your deuterated solvent where there is just a few molecules that have 1 extra hydrogen that should be a deuterium. And we call this proton the residual solvent proton. And the chemical shifts of these residual solvent protons are very well known, and you can find tables of them on the internet. But if you just want to figure out what the multiplicity of your residual solvent proton should be, you can use that same formula, 2Ni plus 1. Whoops. Come on, eraser. My pad is going crazy. Let's grab the eraser here, erase it all out. Alright, so 2Ni plus 1. So we have 2, N is going to be 2, and I for deuterium is 1 plus 1. So that's 4 plus 1 equals 5. So that means the multiplicity that you should see when you run deuterated DMSO, that for that residual solvent proton, it should have 5 peaks on it. So that's not really covered in the book, but it's just a sort of an interesting side note. And then the next topic they talk about is tree diagrams, where you start out with HA, you add in another basically coupling partner we'll call HB, and that will split your signal into two different components. So you'll have a peak here and then a peak here, and this is still going to be at the same chemical shift, but this will be minus a half J coupling, and this will be plus a half J coupling away, and so the distance will be J apart for these 2 peaks. And then if you added in another coupling partner, you would have something like this, where you could say this one is up and this one is up. And remember, this is the spin state of the coupling partner. So this is up and down. And actually, let me do something a little bit different here. So we'll call this guy up and down for HB, and this will be up and down for HB. And then let's change our color. And now if we have an HC here, some HC coupling partner, then this will be up and down, and then up and then down. Oops, I did this totally wrong, didn't I? I screwed up this guy right here. He should be down. So B should be down in this position. So you have B up, up, and then it gets split by the C's, which are up and down. And you have B down, down, and it gets split by the C, which is up and down. And so now you have what you would call a doublet of doublets. Now, when you get these splitting patterns, and I showed you that you have the Pascal triangle, which kind of predicts out the multiplicity of your peaks and intensities. Oops, I forgot one here. Oop. So you got the doublet, you got a single peak, a doublet, then you got the triplet, and then you got the quartet. Okay, so this is for the case what we call weak coupling. And this is what you see in most books, is weak coupling. And so what that means is that this peak, say HA, is a long ways away from, in terms of chemical shift, HB, or what you'll see basically is the frequency of A minus the frequency of B is much, much greater than the coupling constant of AB. So that's the weak coupling case. And in the weak coupling case, your spectrum is predicted by this Pascal's triangle. The other case is when it's not true, when VA minus VB is, less than or equal to JAB. And then we call this strong coupling, which I won't cover in these videos. And the intensities and the number of peaks don't follow Pascal's triangle. I know there's a good book on there about how to interpret strong coupling spectrum, and I'll have to find it because I don't recall off the top of my head what the name of the book was. And as sort of a side note, so here I'm sort of illustrating this whole FID constant, where I've taken I made a data table of a cosine function, and this would be like representing like 1,000 hertz signal, and times it by this exponential decay. And so my T2 is 0.1, and so you see this decay. Now if I make it out to like 10, and then it takes a lot longer to decay, and so I'm just sampling out to 5 seconds. Now if I take that same data and then do a discrete Fourier transform on it, you'll see a nice sharp peak. But if I make it back to 0.1 and then do the discrete Fourier transform, you can see the peak gets a lot broader.